everyone. Welcome to this episode of Foundry Fireside. My name is Renee, and I'm an intern on the Foundry Communications team. I'm here to talk to Dr. Jeremy Demarteau, who works as a project scientist researching recyclable plastics. Dr. Demarteau, could you please introduce yourself?
So my name is Jeremy Demarteau. I'm a project scientist in sustainable polymers at Organic and Macromolecular Facility of the Molecular Foundry here at LBL. I come from Belgium. I have a PhD in chemistry with an expertise in polymer synthesis. After my PhD, I moved to Spain for 2 years for postdoctoral research in plastics recycling and finally landed here in the US. In my part time, I enjoy like playing and watching basketball. I also enjoy like traveling and exploring different national parks.
Plastics are such a critical and prominent part of our lives, and being able to recycle them promotes a sustainable planet and proper waste management. What is the science behind how plastics become reusable monomers?
So to create recyclable plastics, the key is to either develop catalytic systems or to design monomers. Monomers are repeating units of plastics, and those two systems, either the catalytic system or the design of new monomers, can generate like lower energy bonds, making polymer chains easier to break down and entering into a circular economy.
However, plastic waste is still building up. What is currently a major problem in recycling plastics?
So originally, plastics were designed to last for years or even like decades before being disposed of. Now we start to realize that their accumulation in the environment and the challenges with recycling cause significant issues. Consequently, their intended lifetime should be much shorter. And the primary issue lies in the original designs of these plastics, which were not intended for recycling. So breaking down the carbon-carbon bonds between the repeating units has proven to be very challenging in a cost-effective manner. So having functional groups usually helps to break down those polymer bonds.
So, what are functional groups, and how does a lack of functional group contribute to how difficult it is to break down the carbon-carbon bonds?
So if you take, for example, polyethylene that has like a repeating CH2 bonds, so breaking those like carbon-carbon bonds can be extremely challenging, as I said. And as opposite to like the case of polyethylene, PDKs have functional groups that are actually the key to lower this energy to recycle those plastics. Because of the interaction of water and water molecules that can actually like attack at a specific location the diketoenamine bonds and cleave more easily those bonds, we can regenerate the monomer and actually create this circular economy of plastics.
We've kind of been talking about circular plastics. So, what are circular plastics and why do you think they're so important?
So circular plastics are designed to fit into like a circular economy, meaning that they can be fully recycled. When these circular plastics can be like chemically recycled, then the process is known as a monomer to monomer recycling. And this method allows the building block of the plastics to be recovered infinitely after undergoing chemical recycling. That's what is called a closed loop system.
So, as you mentioned, this type of circular plastic that you developed is called a PDK. And how are they made?
So PDK is actually the acronym for polydiketoenamines, and poly refers to the multiple repeating units, while diketoenamine is the functional group within the polymer repeating unit. So PDKs are synthesized using a technique called polycondensation, commonly employed like for the production of polyesters or nylons. And during this process, only water is generated as a byproduct. A monomer called triketone reacts with an amine to form what we call the diketoenamine bonds. And this bond is quite unique because it can be broken down back into the triketone monomer, enabling very efficient recycling at room temperature within a few hours in acid. The solid plastics during the recycling process in acid actually generates a soluble part, that's the amine monomer, and a precipitate being the triketone monomer. So those two monomers can be very easily separated by filtration. And just as a comparison, common plastics like polyesters can take weeks or even like months to be partially deconstructed under similar conditions, whereas PDKs only take like a few hours. So this comparison just highlights the uniqueness and efficiency of PDK chemistry.
So moving on to some more recent research, could you explain what is triacetic acid lactone and how did you discover it and why did you decide to incorporate it into plastics?
So triacetic acid lactone is a polyketide that can be derived enzymatically from glucose. In our research program, we were like looking at very similar molecules than tal, and we actually found out that tal, or triacetic acid lactone, could be incorporated to design our building blocks that I already mentioned, that are the triketone monomers.
Yes, that sounds really cool. So how are you able to use tall to create a circular plastic and how does the science work behind that?
So essentially, we combined tau molecules with different types of diacids to generate the triketone monomers. That was done in a condensation reaction. And once we have isolated the triketone monomers, we were able to achieve this circularity in our PDK plastics that I mentioned.
Yeah, so basically you were able to use tall and combine them using condensation reaction to form the monomers, and that creates a circular plastic, right?
Exactly. So combining these triketone monomers with an amine generates the PDK, and then in acid, you can regenerate the triketone and amines.
That sounds really easy to make and to break back apart.
Yeah.
So incorporating tall also has some other benefits, such as increasing the working temperature of PDKs. What's the chemistry behind this?
The tau molecule, because of its aromatic component and the double bond, creates like a very flat triketone molecule in two dimensions, which actually provides higher crystallinity compared to the previous triketone that we generated in the past. So this higher crystallinity in tau triketone gives like higher stacking of the polymer chains. And so, like in summary, this crystallinity brought by the tau molecule usually gives like very interesting properties to the materials that are generated, like higher working temperature.
Why might this be an advantage for plastics?
So in sectors like automotive manufacturing, the ability like to withstand like high temperatures is actually crucial. So this is because like industrial processes often like require material to reach like high temperature before like those material can flow and be shaped. So without undergoing any degradation.
And that sounds so useful. So overall, what was your research process like?
So we first synthesized the tau monomer, the tau-based triketone monomers that I mentioned. And we actually recycled those PDKs in the lab first as like initial exploratory experiment. We then like ask our collaborators that are biosynthetic chemists that we have like partner in our program to explore actually the bioproduction of tall using modified enzymes or bacteria. And they were able to achieve like high titer for this tau molecule in like a huge bioreactor, like around like 20 liters. And so we incorporated this like bioproduced tau in our recycling process. And at the same time, we also worked with engineers that were modeling this biotau production to assess the cost and environmental impact of this synthesis, which was actually where we were actually able to demonstrate the significant reductions for both metrics, so the cost and the CO2 emissions using this tau molecule compared to what we've done previously.
Yeah, it's so awesome that so many groups are involved in the production of this one process. So speaking more personally about you, your research majorly surrounds recyclable materials, even when you were a postdoc. What inspired you to go into this research?
So as a chemist in the polymer field, I've always been like inspired to, I would say, make a better place using like the materials or creating new materials that we have. So as a postdoc, I started like to challenge myself in like the recycling plastic waste field. And I really enjoy that area, that field. So I moved on to actually design like better plastics with like PDKs right from the start. So it's taking the issue of like plastic waste and on a different side. And for the past 4 years at the Foundry, yeah, I've been dedicated to that mission.
Nice. So this sounds like such a huge deal. And in your opinion, why do you think creating plastics will have such an impact on us, and how might it actually affect our lives?
Yeah, the introduction of circular materials into our lives could definitely like transform the plastics economy, like shifting, for example, our perspective from seeing plastics as waste to recognizing them as valuable material that can be infinitely recovered, and like developing like new designs that are easily recyclable will definitely make a significant impact in this field.
Nice. And what do you think is the next step for PDKs or recyclable plastics in general?
So I would say like the commercialization of PDKs, for example, serving in as application in automotive sector would be the next step for PDK. Currently, there are like 2 startups actively working on in this field and using the PDK chemistry to push the commercialization in that direction.
Awesome. Dr. Demarteau, thank you so much for your time and for your insight. It's really great to learn all about the chemistry of plastics and how it's impacting our lives. Thank you all for watching, and make sure to check out more episodes of Foundry Fireside on our website.